section we're on right now is forms of energy. The 200 kilogram hammer of a pile driver is lifted 10 meters. Let's go ahead and write that stuff down. Mass, 200 kilograms. It's in kilograms. That's good. That's what we need. The distance is 10 meters. Find the gravitational potential energy of the system when the hammer is at this height. Well, our potential energy is mass times gravity times height. Our mass is 200 kilograms times 9.8 times the height, 10 meters. We multiply that all out, and we're going to get 19,600, and energy is in joules. That's number one. Number two, a person weighing 630 newtons, so that's his weight. Weight is a force. I like to do F sub W, whatever way works for you, but this is what I like to do. 630 newtons. He goes up to a height, that's a distance, or we probably are going to want to use height for that. 5.0 meters. What work does he do? And then what is the increase in potential energy? So we want to know what is the change in potential energy. Alright, work, force times distance. Well, the force we're already given, that's good, 630. And the distance, or the new height, is 5. So when we do our work, it's going to be 3,150 joules. Now, our change in potential energy is going to be our final potential energy minus our initial potential energy. Well, if our initial potential energy, if we started on the ground, the initial potential energy is going to be 0. The final potential energy is going to be mgh. But the thing is with this problem is mg, that turns out to be the weight. Mass times gravity is the weight. They've already given us the weight. They have not given us the mass, so we can just take weight times the height, which is 5 meters, and look what we have. We have the same answer here, 3,150 joules. Same answer. Number three, an 8 kilogram mass moves at 30 meters per second. What is its kinetic energy? If the object is initially at rest, how much work was done to give it that kinetic energy? So this must be the final velocity there. So kinetic energy, our formula for kinetic energy, 1/2 mv squared. So 1/2 times the mass times the velocity squared. And when we work that problem, we're going to get 3,600 joules. Now it wants to know what is the work. Well, from the work energy theorem, our work equals the change in kinetic energy. So if we work through here, that is the final kinetic energy minus the initial kinetic energy. Okay? Now, if the initial velocity was 0, and for our initial kinetic energy, we're going to use velocity, we know that this portion becomes 0. So my work is just going to be 1/2 times the mass, which is 8, times the final velocity, 30 meters per second. And when we do that problem, we're also going to get 3,600 joules. That's the same amount of kinetic energy. Number 4. A 15 kilogram mass is moving with a velocity of 7.5 meters per second. There is a force of -10 newtons. I bet it's going to slow down since it's -10. And the new velocity is going to be 3.2 meters per second. What is the displacement of the object? Well, I know the formula work equals change in kinetic energy. And I know that work is force times distance. My kinetic energy, the change in kinetic energy, is going to be the final kinetic energy minus the initial kinetic energy. Let's see if we have all these variables. Force, distance, mass, final velocity, initial velocity. Yes, we have everything we need. So my distance is going to be 1/2 times 15 times 3.2 squared minus 1/2 my mass times 7.5 squared all over the force, because I need to get force away from over here, -10. When I work number 4 out, I should get 34.5 meters. That is 1 through 4. Number 5. What is the speed of a 5.44 kilogram shot put if its kinetic energy is 68 joules? Well, I know that kinetic energy is 1/2 mv squared. What is it that we need? We need the velocity. Let's plug it in. 68 equals 1/2 times 5.44 times v squared. In these problems, a lot of times kinetic energy, the reason why we mess it up is because we forget that square. So don't forget the square. And if we're looking for v, we're not looking for the v squared. We're going to do a square root here in just a few minutes. So for number 5, when I do the problem, move all this stuff around, multiply by 2, divide by 5.44. I'm going to end up with 25 equals v squared. Take the square root of both sides. I think you don't need a calculator for that. The velocity is 5 meters per second. Number 5. Here's number 6. A 50 kilogram cyclist, so that's the cyclist, and then the mass of the bicycle is 10 kilograms, speeds up from 5 meters per second to 10 meters per second. Okay? I'm going to write up here, what's the kinetic energy before acceleration? That's initial. V says what is the total kinetic energy? How much work was done? And then D says, is it more work to speed up from 0 to 5 or from 5 to 10? We'll deal with that one here in a minute. So the first one says, well, what's the initial kinetic energy? Well, the initial kinetic energy is going to be 1/2 m times the initial velocity. So that's going to be 1/2 times, now, what is the mass? The mass is the cyclist plus the bike, so we better add those together. 60 times the initial velocity, 5 meters per second, don't forget the squared. So my initial velocity for this one is, the initial kinetic energy for this one is 750 joules. Now it says, well, what was the total kinetic energy after accelerating? So that means the final kinetic energy, 1/2 mv times the final. So I'm going to have 1/2 times 60, my final velocity was 10 squared. So after I've accelerated, now the kinetic energy is 3,000 joules. The question is, how much work does it take? All right, well, hopefully we can still see this right here. Since I know work is final kinetic energy minus initial kinetic energy, I've already done this part, so it's pretty easy. Just going to plug in. So the work that I have done is 2,250 joules. Now D says, is it more work to go from 0 to 5 or from 5 to 10? Well, it's only a difference of 5 meters per second. But because I have far more kinetic energy whenever I'm at 10 than I do at 5, the more work it's going to take when I'm going from 5 to 10. So that's D. We've worked 1 through 6. Check back, and we will give you 7 through 9. Take care. And we're back with number 7. A steel ball has a mass of 4 kilograms, and it rolls along a smooth, level surface at 62 meters per second. We need to find its kinetic energy. And then part B says at first the ball was at rest, so the initial velocity was 0, so this must be the final velocity. A force acted through a distance of 22 meters to give it the speed of 62 meters per second. What was the magnitude of the force? Well, we're going to ignore this part for right now. The first part, kinetic energy. Kinetic energy is 1/2 mv squared. So we're going to do 1/2 times the 4 kilograms times the 62 meters per second. I'm going to take out our handy dandy calculator here.
7688.
And our kinetic energy is 7688 joules. So that's part A. Part B says we need to find what is the force, magnitude of the force to get it up to that speed. Well, we're going to use the work kinetic energy theorem. So work equals the final kinetic energy minus the initial kinetic energy. And in fact, we're going to go one step further and we're going to say, instead of work, we're going to say force times distance, because that's the formula for work. So since I have force, my distance was 22 meters. My mass is 4 kilograms. The final velocity was 62. It says the initial velocity was 0. If the initial velocity was 0, everything times that is going to be 0, so we can just ignore that part. And once we calculate all this and divide by 22, we're going to get a force of 349 newtons. Number 7. Now number 8. A 2 times 10 to the second kilogram ice boat mass we could also say that's 200 is propelled across a horizontal surface of a frozen lake by the wind. The wind exerts a constant force. I'm just going to call that 400 newtons instead of using the scientific notation. And the distance is 0.90 kilometers. Now I have a red flag right there because in all the energy I've got to use meters and not kilometers. So to go from kilometers to meters, I'm going to move the decimal place over 3 times and I get 900 meters. Assume that frictional forces are negligible and that the boat starts from rest. VI equals 0. What is the boat's final speed? VF. Alright, well, I think I'm going to use the work energy theorem. I know that work is force times distance, and I know that the change in kinetic energy is the final kinetic energy minus the initial kinetic energy. So to find my final kinetic energy, it's 1/2 m times the final velocity squared minus 1/2 m times the initial velocity squared. Alright, let's plug in the things we know, except that we could say since the initial velocity was 0, we can get rid of this stuff. Don't get into the habit of just crossing that out right away, because that's not always going to be the case. So my force was 400, my distance was 900, the mass was 200, and of course I'm trying to find the final velocity. And when we get all these going, multiply and divide, and don't forget we're going to take the square root. My final velocity is going to be 60 meters per second. Here is one part that a lot of people miss, is you have to take the square root of the answer that you're looking for. That's number 8. Alright guys, number 9 is the exact same as the section before number 3. So go back to number 3, that's going to be number 9. You can skip one or the other, either way. Talk to you later.